All right, beginning lesson 2 in our linear regression topic, looking at correlation today. Beginning on this warm-up, describe a possible flaw in the reasoning of each situation. First one, if I wash my hands regularly, I will not get sick. Well, I'm not going to write anything out here, but I'm just going to talk you through it. It's possible people that wash their hands all the time still get sick, so there's a flaw there. It's not directly related to each other. Second one, if I practice my guitar every day, I will be a rock star. Now, practice does help get to where you want to get as a goal, but there's no guarantee there that if you practice every day, you're going to become a rock star. There's still skill and fame involved that's not directly related there. Third one, if I wear my favorite football team jersey to support my team, they will win the game. I wish it worked that way, but it does not. There are a lot of fans that wear a jersey, and then, of course, their team loses. And then the fourth one, if I'm a good driver, I will not have an accident. Again, I wish that was the case, but unfortunately, even good drivers get into accidents. Sometimes they cause them, and then, of course, there's the chance you could have an accident as a driver caused by someone else. All right, so key terms we're looking at here: correlation, correlation coefficient, coefficient of determination, causation, necessary condition, sufficient condition, common response, and confounding variable. All right, so on the getting started activity, it says describe any association between the independent, dependent variables and then draw a line of best fit. Well, for the first one there, we have a trend that is going down from left to right, decreasing. So this would be a negative association. Line of best fit might look something like this. For B, there's no association there. There's no correlation we can see there, so no association. You couldn't look at that and say definitively there's any sort of positive or negative association, so we can't draw a line of best fit. And then C would be a positive association. So line of best fit would look something like that. All right, on to activity 2.1, the correlation coefficient. Measure how well a regression fits a set of data. It's called the correlation, and the correlation coefficient is a value between -1 and 1, which indicates how close the data are to the graph of the regression equation. The closer the correlation coefficient is to 1 or -1, the stronger the relationship between the two variables. Negative would just be it's going down, a negative association. Positive, it's going up. So close to -1 would be a strong negative correlation. Close to +1 would be a strong positive correlation. So if we look at the first one, A, it's a negative correlation. It looks pretty strong. It looks like it's a pretty obvious trend going down. So I'd be looking something closer to -1. So the closest there I see to -1 is that -0.9. Okay, on B, I see a pretty obvious positive correlation. It's pretty easy to look at that and see recognize that it is positive, increasing, going up. So we're looking closer to +1, which I would say would be 0.7. And then for C, doesn't look like I can see any obvious association there, increasing or decreasing. So I would look for a correlation coefficient closer to 0. So that would be something like 0.01. Now, this equation here shows you how the correlation coefficient is calculated, but the good news is that your calculator can do this for you. Now, on your calculator, let me bring up mine here. We want to turn diagnostics on if it's not already on your calculator. The way you do that is you see where the 0 button is in blue. It says catalog. So we want to click the second, if I can get that to go off the screen, 1 second, there we go. Hit second 0 to bring up catalog. And we're going to go all the way down to diagnostics. It's in alphabetical order. And we want to turn diagnostics on. So just click enter on diagnostics on and then enter again. Now, when I go enter data, if you see back on your notes, number 2, it says consider the data set 23, 23, 1, 2, and 3, 4. I can go enter that data like we did in our last lesson for linear regression, hit stat, edit, My x's would be 23, 1, and 3. And then my y's are 23, 2, and 4. And then do linear regression, stat, calculate, option 4, linear regression. And now when we calculate that, it's going to give us two new values there besides our a and our b. We got an r squared and an r. So we'll talk about r squared coming up here in a minute, but you see the r value is our correlation coefficient, 0.999. Very strong positive correlation, very close to 1. So that data set would have a correlation coefficient of 0.999. So that would be a very strong positive correlation coefficient. All right, for activity 2.2, is it linear is what we're looking at. So it says a group of friends completed a survey about their monthly income and how much they pay for rent each month, and the table shows those results. So we got an X column that's monthly net income, Y column that is our rent. So if we're going to identify independent, dependent variables, I'm just going to label them up here on our table. Here's our independent variable, the monthly net income, and our dependent variable, our monthly rent. So we'll draw a little arrow up there to recognize that. So if we want to construct a scatter plot, plotting those points. So let me go through and plot those points. 1,400 to 450. Be there. 1,550, 505 would be about here. 2,000, 545 would be about there. 2,600, 715 would be about here. 3,000, 930 would be about there. And then 3,400, 1,000 would be up here. So we can see our points there. It says, do we think a linear regression equation would best describe this situation? I'd say so. I'd say yes. It appears to be linear, and I'd say it looks like it has a strong positive correlation. Okay, 3, use technology to determine whether a line of best fit is appropriate for this data. So again, I'm going to go back to the calculator and I'm going to input that table from the previous page. Close out our add here. So I'm going to go back to stat, edit, clear out my L1 and L2, put my new X's under L1. That was 1,400, 1,550, 2,000, 2,600, 3,000, and 3,400. And then my Y's are 450, 505, 545, 715, 930, and 1,000. And then back to stat, over to calculate, and down to linear regression. And then we're going to click calculate. All right, so there is our line. We got a slope of 0.28 and an A value, a y-intercept of 36.27. Now, it gives us a correlation coefficient of 0.98. So again, that's a very strong positive correlation. So I'm going to go back and we're going to write that equation now in our notes. So that linear regression line was y equals 0.282x, our slope, plus 36.3 if we round those. Okay, and the correlation coefficient was r equals 0.9817. So would a line of best fit be appropriate for this data? Yes. The r value is close to 1. It is a strong positive correlation coefficient. All right, next we're going to look at the coefficient of determination. There was that r squared we saw in the calculator screen as well. So it says the correlation coefficient r indicates the type positive or negative and the strength of the relationship may exist for a given set of data points. The coefficient of determination, the r squared, measures how well the graph of the regression fits the data. It represents the percentage of variation of the observed values of the data points from their predicted values. So, using that, going to activity 2.3 now, it says the amount of antibiotic that remains in your body over a period of time varies from one drug to the next. This table shows the amount of antibiotic X that remains in your body over a period of 2 days. It says determine and interpret a linear regression equation for this data set. Now again, we would put that in the calculator just like it did before, so I'm not going to go back to the calculator screen. I'm just going to list out what we get as a result when we do the linear regression in the calculator. So the equation we would get is y equals negative 1.1x plus 42.3. Okay, I would pause the video, do regression in your calculator, and make sure you can get that linear regression equation. Now, the correlation coefficient and the coefficient of determination. So the R value, the correlation coefficient, is negative 0.88. So we got a pretty strong negative correlation coefficient. But the R squared value is 0.780. So, does it seem appropriate to use a line of best fit here? Okay, I would say no. An R of negative 0.88 and r squared of 0.780 are not extremely close to 1 or negative 1, respectively. Now, you'll remember on that one earlier, that first one we did, that first example from the calculator screen, we had an r before we talked about what r squared meant. Both the r and the r squared were both 0.99. That would more relate to a strong coefficient of determination that represents a linear function. Okay, and if we sketch this, we're going to see why here. If we sketch this data, 0.60 would be here, 6.36 would be about here, 12.22, 18.30 or 18.13, I should say, would be about here. 24, 7.8 would be about here. 30, 4.7 would be there. 36, 2.8 would be about here. And 42, 1.7, I'll stop there at that point. And what we see there, the reason why it didn't have a very good coefficient of determination is what we have is actually not a linear graph, it is an exponential graph, okay, which makes sense. You talk about antibiotic in the body over time, it's going to exponentially decrease, exponentially decay out of the body. So, looking at that graph, it says, do we still agree with our answer from above? I'd say yes. It appears to be exponential. Sorry, all that deleted. I clicked wrong. So if you need to see that, just rewind the video. I'll rewrite the answer here for 5. So yes, it appears to be exponential. Not linear. All right, activity 2.4, correlation versus causation. Okay, does correlation necessarily mean there's a causation? We could see a correlation in the trend of a data, but not necessarily making one factor cause the other one. So causation means we have a direct cause of the second variable happening. So we're going to read through these statements and we're going to determine would this be correlation or causation. So for number one, the number of smartphones sold in the United States increased every year since 2005. The number of flat screen televisions sold in the United States has also increased during the same period of time. So they're both increasing, so we could say there is a correlation, but there's other factors involved there. We can't necessarily say that because people bought more smartphones, that caused people to buy more flat screen TVs. So not causation, but we would have a correlation there. So two, since 2004, the average salary of an NFL football player has increased every year. The average weight of an NFL player has also increased yearly since 2004. So they're both increasing again. So that data would look like there's a correlation. But we can't say that because their salary is increasing, their weight is being caused to increase. So there wouldn't be causation there. And then for number three, worldwide, the number of automobiles sold annually has steadily increased since 1920. Gasoline production has also steadily increased since 1920. Now we come across one would be reasonable to conclude that there is causation there. If we have more automobiles, we are going to need more gas. So having more automobiles would cause a need for gasoline production to be increased. So there would be causation, not just correlation. All right, so causation is when one event affects the outcome of the second event. A correlation is just a necessary condition for causation. So there needs to be correlation for causation to exist, but not the other way around. Correlation is not a sufficient condition for causation. So just because on this, like those examples we saw before, that there was a positive correlation, both of the factors were increasing, it doesn't necessarily mean that's a necessary or sufficient condition to show causation. So if we look through these examples now, number four, many medical studies have tried to prove smoking causes lung cancer. A, is smoking a necessary condition for lung cancer? Well, smoking can increase your risk of lung cancer, but there are people that get lung cancer that don't smoke, so it wouldn't be a necessary condition. So I'd say no. People that don't smoke have also had lung cancer. There are other causes. Okay, is smoking a sufficient condition for lung cancer? So again, if it's not directly, so we would say no. Because not every person who smokes gets lung cancer. So that alone is not a sufficient condition. So C, is there a correlation between people who smoke and people who get lung cancer? Yes, there is a correlation because smoking does increase your risk of lung cancer. And then D, is it true that smoking causes lung cancer? So yes, it has been proven that smoking can cause lung cancer. But it is not the only factor that can also cause lung cancer. But it has been proven that it can cause lung cancer. Okay, another example here. 5 is often said that teenage drivers cause automobile accidents. So for A, is being a teenage driver a necessary condition to have an automobile accident? Well, no, there's plenty of drivers that are not teenagers that have accidents. So no, all drivers have accidents. Is being a teenage driver a sufficient condition to have an automobile accident? So again, that alone is not a sufficient condition. So no, not every teen has an accident, has a car accident. C, is there a correlation between teenage drivers and automobile accidents? Correlation, yes. Teenage drivers do tend to have more accidents. So there is a correlation. And D, is it true that teenage drivers cause automobile accidents? So yes. I'd say they do have more accidents. But again, it's not a sufficient condition because there's other drivers that aren't teenagers that also cause automobile accidents. Okay, for the next example, it says, does school absenteeism cause poor performance at school? A correlation between the independent variable of days absent to the dependent variable of grades makes sense. However, this is not alone does not prove causation. In order to prove that the number of days that a student is absent causes the student grades to get poor, we would need to conduct more controlled experiments. So A says list several ways that you could design experiments to attempt to prove this. Well, you could create a table and track absences compared to grades. I think that would be our most obvious one. Okay, it would also maybe show not only those that are absent a lot, are they performing poorly, but are there people that are not absent that it's proven that they're performing much better? See if there's a correlation or is a cause there. And B, will any of these experiments prove the assertion? Well, could possibly prove it. It also could show just correlation, but it might also show causation. It's going to depend on the data set we have. You might have data from a group of students that looks like it directly does cause it. You might have a data set from students that show students that are not absent that also perform poorly, to where there's not a causation between the two. All right, on to the next page. There are two relationships that are often mistaken for causation. The first one being a common response is when some other reason may cause the same result, or a confounding variable is when there are other variables that are unknown or observed, which happens quite a bit. So consider each relationship and list two or more common responses that could cause this. In North Carolina, the number of shark attacks increases when the temperature increases. Therefore, a temperature increase appears to cause sharks to attack. Well, first thing I would think of, when the temp increases, more people go swimming at the beach. You could also say, oops, sorry, that went away. You could also say more people in general are on beach vacations when it's hot. So the outside factors would be simply that there's more people in the water when the temperature goes up. If the same number of people were in the water when it was cold out, you might have an equal number of shark attacks. So the temperature alone isn't causing the sharks to attack. And for B, a company claims their weight loss pill caused people to lose 20 pounds when following the accompanying exercise program. Well, they just listed an extra factor there in the statement. People might also exercise. So the people are exercising. Again, rewind it. I accidentally hit the button to delete that. So people are exercising. And another factor they don't listen, people might be dieting. Or we'll put changing their diet, which is not mentioned in that statement, which diet alone has just as big an effect as anything listed there between their weight loss pill and an exercise program. All right, and then to wrap it up on the next page, good time to pause the video and try both set A and set B. Use your calculator to see if you can come up with those linear regression lines and the correlation coefficient and the correlation or the coefficient of determination. Okay, then unpause the video. I'm going to list out what your equations should be and see if you're getting the correct data from the calculator. So for number 1, we should have got y equals negative 1.15x plus 20.71 with a correlation coefficient of negative 0.9512 and a coefficient of determination of 0.9048. And then for set B, you should have got an equation of y equals 5.08x minus 43.29 with a correlation coefficient of 0.7892 and a coefficient of determination of 0.6228. Okay, and then 2 wants us to compare the correlation coefficient and the coefficient of determination in each data set, describe which regression equation is the better fit. Well, if we look at those correlation coefficients, it's quite obvious that set A is a better fit because that R value is close to -1 at -0.95.